next we will discuss on stuck at faults. So, when a line is stuck at a particular value, when we are talking about digital circuits, so naturally this stuck at value can be stuck at 0 or stuck at 1. So, it is taken as the line is permanently 0 or permanently 1. So, this may be manifestation of some defect like a line getting shorted with the supply line, power supply line. So, that way it is stuck at 1. Similarly, a line getting shorted with the ground line. So, that may be reflected as a stuck at 0. So, the physical defects are modeled as these faults, stuck at 0 fault and stuck at 1 fault. So, in under this stuck at fault model, number of fault types, that is k equal to 2. So, this is an example circuit where you can see that okay, we have got if 2 AND gates, 1 OR gate and 1 inverter. So, it is realizing the function A B or B bar C. Now, in this case, so there are altogether 9 lines. So, the fault sites equal to n equal to 9. So, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So, there are 9 points at which their fault can occur. So, this all this A, B, C, D, E, F, G, H, I. So, they are identifying them. Now, so each of these lines it can be permanently stuck at 1 or permanently stuck at 0. As a result, there can be 2 faults associated with every line. So, altogether if I consider only single faults, so there are 2 into 9, that is total 18 faults are possible. Now, if we just consider the truth table for this for occurrence of these faults. So, this x 1, x 2, x 3. So, this side we have listed all the inputs, all possible input patterns that can come. So, this next line y, next row y. So, it identifies the fault free responses. So, if there is no fault in the circuit, so this is the type of response that we get. Now, if A is stuck at 0, if A is stuck at 0, then this particular pattern 0 0 0, the response is same as the original good circuit, because A is stuck at 0 and in this case I am applying 0 to x 1, that is 0 to A. So, naturally there cannot be any distinction. So, all these cases 0 0 0 to 1 0 1, the response remains same as the good circuit. However, for these two patterns 1 1 0 and 1 1 1, the pattern, the result is different. So, value of y is different. In this case good circuit is 1 and bad circuit is 0, similarly here. So, we see that this truth table, from this truth table we can identify all these boxes where it has been colored gray. So, though where there the response is differing from the good circuit response. So, that way that fault can be detected by the corresponding pattern. Now, faulty circuit differs from good circuit. So, if the test vectors are valid test vectors, like this 0 1 1 is a valid test vector when we are talking about this A stuck at 1 fault. So, the fault free response is 0 and faulty response is 1. Now, some vectors they are termed as necessary vectors. So, necessary vectors are those vectors that are must for detecting some fault. For example, this F stuck at 1. So, this F stuck at 1 fault. So, this is detected by this particular pattern 0 1 1, and if you look into this row carefully, you will see that none of the other test patterns can detect this particular fault F stuck at 1. So, that way F stuck at 1 becomes a necessary vector. So, any test vector set that does not include this particular pattern 0 1 1. So, for that test vector set, it will not be able to detect this particular fault F stuck at 1. So, that way it is a necessary vector. Similarly, E stuck at 0. So, that is also detected by this particular vector. So, E stuck at 0. So, this one. So, here also it is detected by 0 1 1. So, that way 0 1 1 becomes a necessary vector. Similarly, 1 0 0 detects D stuck at 1. So, all together, so can detect total of 10 faults, and this 0 0 1 and 1 1 0 detect the remaining 8 faults. So, this is the all the in this case we are lucky, because applying this test pattern set. So, all 0 to all 1, we could detect all possible faults in the circuit. This has happened because the circuit does not have any redundancy. If the circuit had redundancy, then of course, this will not be the case. For there will be certain faults which will not be detected whatever test pattern we apply to the circuit. But in this case, this is not redundant. As a result, we could detect all the faults. Now, another thing is the set of equivalent faults. Now, there are certain faults like say this A stuck at 0 and D stuck at 0. So, if you look into these two faults, you see that their responses are exactly same, their responses are exactly same for all the test vectors, like it is 0 1 0 0 0 1 0 0, here also it is 0 1 0 0 0 1 0 0. So, that way responses are same. So, with in none of these test pattern can distinguish whether a fault that has occurred, whether it is A stuck at 0 or D stuck at 0. So, these two faults cannot be distinguished. So, that makes an equivalent class of faults. So, if we look there are more such faults like say A stuck at 0, then this D stuck at 0 and G stuck at 0, they form one equivalency class. Similarly, we have say these faults G stuck at 1, H stuck at 1 and this one this I stuck at 1. So, they form another equivalency class, because for all the applied test patterns the responses are same. So, we cannot tell distinctively the which fault has exactly occurred. So, we cannot distinguish between all those faults. So, these faults are equivalent faults. So, there is no point trying to differentiate between equivalent faults. So, we from this equivalent set we can consider only one fault for test generation, and knowing fully well that the remaining faults are also detected by this pattern, though we cannot say very distinctively which one of them have occurred. Now, you can come up with a formula that says the number of such collapsed faults. So, collapsed fault means when you have removed all these equivalent fault from all equivalency classes, I have taken only one fault. So, in that case the number of collapsed faults is given by 2 into primary input plus fan out stems plus number of gate inputs minus number of inverters. So, this formula it can give us the number of collapsed faults in a circuit. So, in the previous example that we had, so number of collapsed fault equal to 10, primary input is 1. So, there is only one primary output is 1, the Y only. Similarly, fan out stem is 1, because there is only one point where there is a fan out. So, this point there is a fan out. Then we have GI equal to 7, GI is the number of gate inputs. So, 1 2 3 4 5 6 and this inverter 1 7. So, there are 7 inputs that are there. So, and Ni number of inverters equal to 1. So, if you put into this formula, the value turns out to be 10. So, that way this formula can give us number of collapsed faults for any circuit under stuck at fault model. Fault collapsing is very important, because it can be seen that it can reduce the number of faults by 50 to 60%. So, that is a huge saving. So, if we have a big circuit and it has got a large number of lines and gates in it, a large number of fan outs in it. So, as a result the number of faults will be very high. So, this if we can collapse if we consider the collapsed fault set, then the faults may come down to 50% of the original one. So, as a result it can reduce this faults significantly, number of faults significantly. Next, we will look into the transistor faults. So, at the transistor level, so if you consider, so a transistor can be stuck short or a transistor can be stuck open. So, stuck short means there is a short between this drain and supply drain and source lines, and stuck open means there is a this transistor is open. So, this connection is not there to the gate. So, as a result whatever input we apply here, that does not reach this gate, and until and unless this gate gets enough potential, no channel is established between the drain and source. As a result the transistor is taken as open. So, there are two types of faults that we will consider for transistors. One is called stuck short fault, another is called stuck open fault. So, here also K is equal to 2, and for this example circuits number of there are 4 transistors. So, 4 transistors, so there are 4 faulty sites, n equal to 4, and number of single faults. So, each of them can be stuck open or stuck short. So, total number of faults is 2 into 4, that is 8. Now, if you apply some test pattern like say A B are the 2 inputs to this NOR gate, 2 input NOR gate. So, this 0 0 0 1 1 0 1 1. So, these are the combinations. So, in under fault free condition, so this is the output 1 0 0 0. Now, if N1 is stuck open, so this transistor is open. So, whenever A is equal to 1, so whenever A is equal to 1, so this case, so this transistor will not be able to conduct. So, if this transistor is unable to conduct and N2, if N2 is 0. So, if N2 is 0, that means there is no path through this N2. As a result, this point Z, so it will continue to remember its previous value. So, there is no discharging path for this Z. So, as a result, Z will continue to remember its previous value. That is why N stuck at open. So, this last Z value will be remembered. Similarly, if N1 is short, then whatever whenever we apply say 0 0. So, this point will get some this point Z will get charged to 1. However, since this transistor is short, so there will be a current flow through this. So, if we detect this current flow through this IDDQ test, so we will come to that later. So, we can measure the quiescent current flowing through the device, and ideally if the transistors are all okay, then when putting A and B both equal to 0, these transistors will be off. So, only a very small amount of leakage current should flow from through these transistors. So, but if this transistor is stuck short, then naturally the amount of current flowing will be larger. So, this way this IDDQ test can measure the current that is flowing through the device, and accordingly it can detect if there is a fault in the transistors. So, this way all these transistor faults can be characterized, and we can infer like which of them have occurred by looking into the corresponding patterns and the responses. So, the stuck short faults caused conducting path from VDD to VSS, as we have already said. So, can be detected by monitoring steady state power supply current IDDQ. So, this is the IDDQ is the current flowing through the device. So, if there is a stuck short, then we can do this thing. Stuck open faults, it will cause output node to store last voltage level, that we have seen, like this transistor is open and this is off, then this will remember the last value. Now, if we want to detect this stuck open faults, then naturally we will require two vectors, okay, because first of all this Z, it should attain some voltage level. So, that has to be done. So, for that pattern, for that purpose we have to apply 0 0 here. So, that these two transistors are on and this Z gets charged to some value, and after that we apply 1 0. So, that we expect that Z will get discharged via N1. So, if N1 is stuck open, then naturally the discharging will not happen. So, it will remember the previous value. So, the stuck short fault can be detected by this IDDQ test, and this stuck open faults, for that we need to apply two successive test patterns, for one for exciting the fault and another for detecting the fault. So, in case of transistors, so you can come up with a formula, number of collapsed faults is twice number of transistors minus number of series transistors plus number of groups of series transistors, number of parallel transistors and number of groups of parallel transistors. So, you can put into this formula and see what is the number of collapsed faults. So, for this particular circuit that we are considering, so we have got 4 transistors, number of series transistors is 2, GS is the number of groups of series transistors, one group of series transistors, so that is 1, TP is the number of parallel transistors, so that is again 2, and GP is the number of groups of parallel transistors, that is equal to 1. So, if you put into this formula, it turns out to be 6. So, there are 6 equivalent non-equivalent faults that we need to consider. Again, fault collapsing can reduce number of transistor faults by 25 to 35%. So, that is a huge reduction in the number of faults, assuming the considering the fact that a circuit, when you are considering at a transistor level. So, at transistor level the number of transistors is much higher compared to say the corresponding gate count when you are considering the stuck at fault model. So, naturally 25 to 35% saving is saving large number of transistor checks. For the wires, so wires may be open or wires may be shorted. So, open wire means it the interconnecting opens in wires interconnecting transistors to form gates behave like transistor stuck open fault. So, if we open if a line is broken, okay, so it will behave like transistor as if that, okay, it has got one side of it. So, if this is a wire and there is a break at this point. So, this side I have got one part, this side I have got one part, and then this is, and as if it can be modeled as a transistor fault, because if there is a gate here, if I apply some gate voltage, then this channel will get established. So, as a result, this will behave as a transistor in that case. So, we can say that this opens in wires interconnecting transistors to form gates behave like transistor stuck open faults. Similarly, opens in wires interconnecting gates to form circuit behave like stuck at faults. So, if I have got one line, say this is a gate output connecting another gate input. So, if this line is open, then it is like this. So, this is depending upon the logic, depending upon the technology family that we are considering. So, this line is open. So, this line is open. So, this can be treated as logic low or logic high depending upon the technology we have. So, this will also this will behave as if the line is permanently stuck at some value for the second gate. So, when it is interconnecting gates, it is behaving like a stuck at fault. When it is interconnecting transistors, so it behaves like stuck open transistors. So, naturally we can have test vectors for detecting transistors and stuck at faults for checking this wire faults, wire open faults. Similarly, shorts to an adjacent wire. So, two wires may be shorted. So, I have got one wire running like this, another wire running like this. While physically manufacturing this thing, maybe the thickness of these wires are not maintained, could not be maintained very accurately. So, as a result, maybe this part becomes something like this, and this is thick, and similarly this part becomes thick like this. So, as a result, there is a shorting between these two lines. So, that way it gives rise to something called a bridging fault. Now, what happens under this bridging fault? So, like here I have got this A and B as two lines. So, there is a connection established between them through the creation of the bridge. Now, depending upon the technology that we are using, so there the manifestation may be of different types. Like we can have this wired and or type of connection, there will be dominant connection and dominant and or connection. Like say this one, this is wired AND connection. So, AS and BS, as if these two values have been ANDed and the result is available at AD and BD. So, if AS and BS both are 1, then AD and BD are both are 1. If one of them is 0, then these both the destination values they become 0. So, this is wired AND connection. Similarly, there may be situation where we get an wired OR connection. So, wired OR connection will be as if this source and two source values will be ORed and the result will be available at the both the destinations. So, both the destination get the same value. So, that is the wired AND OR type of fault. Then we can have a dominant fault where we say that one line dominates over the other one. So, this A line dominates over B line. So, that is as if it can be modeled as if there is a connection established with this A line and this B line is broken at this point. So, A dominates B. Similarly, we have B dominates A. So, like this. So, then we have got dominant AND OR faults. So, A dominant and B. So, A is there and B is there, and this ANDing of them it is becoming the B's destination. A continues with the previous value. So, unlike this wired AND connection where it was just it was affecting both the lines, here the shorting affects only the B line, not the A line. Similarly, this A dominant or B. So, this connection, so this will the B line will get dominated by A, and this A continues to it at its previous value, but this is dominated by this OR function, and the other way B dominant A and B dominant or B dominant and A and B dominant or A. So, these are possible. So, accordingly we can get this truth table, and in this case also if we want to detect this type of faults, then we have to take help of this IDDQ testing, which measures the current flowing through the line. So, these are the different types of faults that we can have, and you see that this wired AND connection. So, in this case, so this both of them becomes 0, whereas these destinations are supposed to be 1. Okay. So, that way it can be detected. Another class of faults which are known as delay faults, and also there is something called a crosstalk. So, delay fault means a circuit as far as its function is concerned, it functions properly, but the timing is a problem, like it does not produce the output within the desired time. So, it has got problem because if the output of a certain stage of logic does not come up within the desired time. So, when that output is fed as input to the next level, so it may be that next level will be considering the value before it has settled. So, as a result we have got problem in the setting of values. So, that type of fault. So, they are delay faults that are occurring. So, delay fault can be modeled using cumulative propagation delay, that is one type of fault, and there may be delays and glitches. So, that can be caused by crosstalk. So, crosstalk means when there are two lines running parallelly, then these lines may be one line value may be affecting the other line. So, we have got path delay fault. So, path delay fault is the cumulative propagation delay through the circuit. So, there are for detecting such faults. So, we have to have two test vectors. The first test vector will set the value output value at some point, like say in this particular case. So, if we apply the pattern 0 1 1. So, this value becomes 0, this value becomes 1. So, sorry, this value is also 0 1 1. So, this is inverter. So, this also becomes 0. So, as a result overall I get a value of 0 at the output. And now, if I apply the pattern 0 0 1, and this inverter has got some amount of delay. So, 2 unit, whereas this AND gates they have got delay of 3 units, and this has got a delay of 2 units. Then for some amount of time. So, it will be so that though the result is expected within this, if the delay was not there, the result is expected immediately, but now the result will come after time 7. At t equal to 7 this transition occurs, whereas at t equal to 0 the output has the input x 2 has changed from 1 to 0, but in at t equal to 7 only we get this. So, this is the delay that we have. So, that delay may or may not be acceptable depending upon the circuit specification. Why this thing happened? This thing happened because due to the delays of individual gates, plus if I have got a number of lines running parallelly, signal lines running parallelly, then there may be the effect of one line coming on to other lines. So, one line may force other lines transition either positively or negatively. Another type of faults which are common in memories. So, they are called pattern sensitivity and coupling faults. They are common in high density memories. So, pattern sensitivity fault. So, this actually what it says is the content of a memory cell is affected by contents of neighboring cells, and there is a coupling fault which says that the transition in contents of one memory cell causes change in the contents of another memory cell. So, what we actually mean is, suppose this is a memory. So, memory is bit organized. So, these are the rows and say these are the columns. Now, if we are considering say value at this point, value at this cell. So, it may be that due to some manufacturing defect I cannot change this independently. So, if I want to put, if this value, all these values are say 1 and say this value is 0, then this value automatically becomes 1. So, that way there is a pattern sensitivity fault. So, certain pattern in its neighborhood may force a point to go to some other value. And another difficulty is the transition fault or coupling fault, means if I want to change a location's value, again it's the same thing. Suppose I want to change this location value from 0 to 1, it may so happen that when I am doing this thing, so this location value also changes. Okay, so, this is known as the coupling fault. So, this it is common in memory cells of high density RAMs, and this pattern sensitivity fault. So, the contents of cell affected by contents of neighboring cells, and this coupling fault means the transition in one cell causes change in another cell. Now, how to detect this type of faults? For detecting this type of fault, so we have to we have got a special type of testing technique which are specific for memories, which so one such testing is known as merge test. So, in merge test, what we do, we write some pattern to the memory cells and try to read the content and see whether this has been checked properly, this has been done properly or not. So, this is one possible merge test sequence. What it says is W0 means I will write 0, and then this up arrow and down. So, so if there is an up arrow means I will be writing in increasing order address. Similarly, this down arrow means I will write in the decreasing order address. So, it says that if we it can, since it is a both directional bidirectional arrow. So, I can just do it in any sequence that I want. So, if I decide that I will do it in the upward address direction. So, first for the lowest cell I will write a 0 there, then the next cell, then the next cell, this way I will go on writing all the cells the 0 values. Then once it is done, I will come to the next element. The next element cell tells that from the highest address to the lowest address, we first do a read operation, and in the read operation we are expecting a 0 to be read, because previously we have written a 0, and after reading this 0, that cell's content is changed to 1. Okay. So, it is basically checking whether these zeros have been written properly, and then it is trying to change this 0 to 1. Then once I have written the entire memory, checked and written the entire memory, now in the increasing address direction I try to read the value, and I am expecting the value read to be 1. I try to write then I write a 0 there, then do a read operation on that cell expecting it to 0, another read operation. So, basically if one read operation distracts the content of the cell, so that will be detected by this particular test, because I am reading 0 then again reading 0. So, two read operations, they should give me the correct values, then this write one will be done. So, this way I can design a test sequence which can detect many of the faults in the circuit, okay, in the memory cells, and that is without any background data. For word oriented memory, so there is another issue where we have to put some background data sequence. So, here I have to give this background data, that is previously it was 0, similarly previously it was 1. So, like that I have to put some background data also. So, we will come to that in detail when we go to the memory testing. Okay, stop here, continue in the next lecture.